Can you rebuild a tree from just its travel diaries? Construct binary tree from preorder and inorder traversal is a pattern mastery 100 cornerstone, regularly asked at Amazon, Apple, and Google to test your deep understanding of recursion and tree building. Over 35% of candidates miss subtle index bugs or don't manage recursion boundaries right. Let's break it down so you don't. We'll use the basic method to solve construct binary tree from preorder and inorder traversal, giving you a powerful template for any tree reconstruction problem. Let's break this down. Given two arrays representing the preorder and inorder traversals of a binary tree, with no duplicates, reconstruct the original binary tree. Input: preorder. Nodes visited as root, left, right. Inorder. Node is visited as left, root, right. Output: root of the reconstructed binary tree. Here is a real-world example. Imagine restoring a company's org chart from two different reports, one listing employees as visited in order of management, preorder, the other listing them by their department or hierarchy, inorder. Interviewers might ask, how would you reconstruct a configuration or parse tree if you only had two traversals? Let's assess. What's tricky? You must know how preorder and inorder traversals uniquely determine a tree. The first value in preorder is always the root. In inorder, everything to the left of the root is the left subtree. Everything to the right is the right subtree. Think step by step. Use a pointer or index to track the current root in preorder. Use a hash map to quickly find root positions in inorder, to split left and right. Recursively, pick root from preorder. Find its index in inorder. Recursively build the left subtree, from inorder left split. Recursively build the right subtree, from inorder right split. Advance the preorder pointer at each recursive call. Let's clarify. Always slice the inorder array to define subtrees. Preorder's root pointer moves forward every time you build a new node. Base case: if there's nothing left to build, left index greater than right, return null. Edge cases: empty lists should return null. Single node builds a leaf. Deeply skewed trees, for example, all left or all right children. Here is the structure. Build a hash map of value index for inorder for O1 lookups. Create a recursive function with left/right boundaries for inorder. At each call, use the current preorder index for the root value. Increment preorder index for the next call. Recursively build left subtree, inorder left split. Recursively build right subtree, inorder right split. Return the constructed node. Now let's implement the recursive reconstruction, using an index map of the inorder array to quickly locate root positions and rebuild the tree. Class setup: this map will store each value's index in the inorder array. It allows us to instantly find where each subtree begins and ends. We store the preorder array in a variable so our recursive method can access it easily. This pointer tracks which preorder element we're currently using as a root. Every time we build a node, this index moves forward. Build tree method. This method kicks off the entire tree building process. We store the preorder array so we can read from it inside the recursive builder. We fill the map with value index pairs from the inorder traversal. This gives us fast, O1 access to each root's inorder position. We start building the tree by considering the full inorder range, left index 0 to right index n1. Build method: recursive constructor. This recursive method builds a subtree using the inorder segment from L to R. If the left boundary passes the right boundary, the subtree is empty. We return null. We read the next preorder value, which is always the current root, increment the preorder index, and find where that value appears in the inorder array. We create a node for this root value. Build left subtree. The inorder segment to the left of M contains all nodes in this root's left subtree, so we recursively build that part first. Build right subtree. The inorder segment to the right of M contains the right subtree, so we build that portion next. Finally, after attaching both subtrees, we return the fully constructed root. And that's how this algorithm works. It first maps inorder values to their indices for fast lookup, then uses preorder to pick each root and recursively splits the inorder range into left and right subtrees. Efficient, simple, and elegant. Let's test our tree reconstruction using these traversal arrays. Preorder tells us the root first order, and inorder shows how the tree is arranged left to right. From preorder, 3 is the root. In inorder, 3 splits the tree into left, 9, and right, 15, 20, 7. We recursively rebuild each side, and the right subtree expands into 20 with children 15 and 7. This gives us the structure shown in the expected output. And that's exactly what our program constructs. The output matches the expected tree. So, our implementation is correct. The reconstruction logic follows the traversals accurately. Now let's implement the iterative stack-based method, constructing the tree step by step by tracking how nodes relate through preorder traversal. Build tree method. We begin with a quick check. If the preorder array is empty, there is no tree to construct, so we return null. The first preorder value is always the root of the entire tree, so we create that node up front. We create a stack to help us keep track of the nodes whose children we still need to attach. We push the root onto the stack so we can begin building downward from it. We start a pointer j to walk through the inorder array. This pointer will tell us when we've finished constructing a left subtree and should start attaching right children. Looping through preorder values. We loop through preorder starting at index 1, creating and connecting each new node. For each preorder value, we create a brand new tree node. Case 1. Attach node E as left child. If the value on top of the stack does not match the current inorder value, it means we're still traveling down the left subtree of the current node. So we attach this new node as the left child of the top node in the stack. We push this new node onto the stack. We'll continue building below it. Case 2. Attach node as right child. If the top of the stack does match the inorder value, it means we've reached the end of a left subtree and must start attaching right children. This variable will help us remember the last node popped, the one we will attach the right child to. While the stack's top continues matching the inorder array, we pop nodes off. This simulates climbing back up toward the correct parent. We save the node being popped. This is the most recent completed subtree route. And we move the inorder pointer forward, marking progress through that traversal. Once popping is done, we attach the newly created node as the right child of the last pop node. We push this new node because it may have its own children later on. Return final tree. After connecting all nodes from preorder, the entire binary tree is complete, so we return the root. And that's how this algorithm works. It first walks down the preorder list attaching left children, then uses the inorder list to know exactly when to climb back up and attach right children. Efficient, simple, and elegant. Let's test the reconstruction on this simplest case. Both traversals contain just one value, which represents a single node tree. The root is clearly -1, and since there are no other elements in either traversal, it has no left or right children. So the constructed tree is just one node. And that's exactly what our program outputs, -1, matching the expected result. So, our implementation is correct. The tree is rebuilt exactly as the input describes. Rebuilding a tree from its travel diaries sounds tricky, but with preorder and inorder you've got a perfect roadmap. This is a classic interview favorite because it exposes whether you truly understand recursion, boundaries, and tree structure. Let's do a recap. We're given two traversals of the same binary tree: preorder, root, left, right, and inorder, left, root, right. The goal is to reconstruct the original tree. Think of it like restoring an org chart from two reports, one in visit order, one in hierarchical order. We leaned on two core truths. The first item in preorder is always the root, and in inorder, everything left of that root is the left subtree and everything right is the right subtree. The main pitfalls? Mismanaging indices and not respecting subtree boundaries as recursion unfolds. Our plan: create a fast lookup from value to its position in the inorder list. Use a moving position in preorder to pick the next root. Then, with left/right bounds in the inorder range, recursively build the left subtree from the left side of the split and the right subtree from the right side. Stop when the current inorder window is empty. We followed that blueprint, advancing the preorder position each time we formed a new node and using the inorder boundaries to keep each recursive call in its lane. No extra slicing work, just clean boundary management. We ran the solution on LeetCode. It constructed the sample tree correctly, handled empty input as null, built a single node tree for the one-element case, and coped with skewed trees. All tests passed without errors and the logic behaved exactly as expected. The big lesson: tree reconstruction is all about disciplined boundaries. Anchor each step on preorder's next root. Let inorder define the left/right regions, and let recursion do the assembly. Get the indices right, and the entire tree falls perfectly into place.